Hey guys, welcome to the fifth and final video in this tutorial series. So today, what we're going to try and do is create a rain or a snow simulation, whichever you prefer. So it's going to look something like this, okay? And so here we're going to make use of everything that we've learned through the series. We're going to apply vectors, and we're going to have a while loop, a whole bunch of different things. Okay, and then at the end you guys can play around and make it fancy and tweak a bunch of parameters. Okay, so let's get started. Let's create a new script. In 5, we're going to start by preparing our workspace. Remember, CRC clears our command window, clears our workspace, and then close all just closes all the figures. That way, the only figure that's open are those ones that we open in this program. Okay, so now let's set a couple of parameters. Okay, so we're gonna first start by setting the number of points. Let's just go with 100 for now. We're now going to define some world parameters. Okay, so this is going to include the map width. Let's set it to be 500. Map height. Let's set it to be 300. So these are things that you can change as well. I'm going to define gravity. Now I've played around with this a little bit beforehand. I think gravity of -1.2 works just fine. And then we're going to add some wind. The wind velocity is going to be 0.5. Okay. Next we're going to have to initialize particle positions. Their velocities. So we're gonna decompose the velocities and positions into x and y. So cos x and cos y. Okay, so the velocities, we don't want them to start with any velocity, so it is going to be 0. If you guys remember the zeros function, it's going to define the size, so we're going to have this many number of points, one column. There we go. And our positions for x. Okay, so we're going to use the linspace function. So I'll show you what that does. The linspace function just creates linearly spaced values between some starting and final value, and it's going to be this many number of points. So let's say that we want to start at 0. We want to go to the map's width, and we need, okay, so all our points are going to be distributed uniformly from our starting position to our ending position, and it's going to be 1 point per uniformly distant point. They're all going to start at the very top. Okay, so how might we want to do that? Well, there's this other function. So just like the zeros creates a matrix of zeros, there's this other function called ones. Guess what I might do? Does the exact same thing that zeros does, except instead of zeros, it creates ones. Now you might wonder, does that mean there's a function for 2s, 3s, 4s, and so on? No. And why not? Well, the reason is because we can just create this ones function and then scale it up by some constant, right? So we can go, we want to set at the very top, so map height, we're going to create ones, we're going to go number of points, one column. Okay, so there we go. I'm going to put everything at the very top. Okay, so we've initialized our particles' positions. Their velocities are initialized. That's it for the setup. Now let's run our simulation. Okay, so what are we going to do? I'm going to open up the figure. Remember that code from before for defining the figure? I'm just going to copy it. Okay, because I want the figure to be nice and large. Okay. There we go. And now we're going to run our simulation. How are we going to do that? Well, we want simulation code, which is going to happen here, to keep happening until we tell it to stop. So remember that I told you a while statement continues to run until the statement inside here is false. Well, we can just trick this code into always running by setting it as 1. So remember, 0 is false and 1 is true. So as long as we've got always this true, this code's always going to run. So if we run this now, it opens up the figure, but it doesn't have time to display it yet because this code's just always running. Okay, so you can see that this command window is inactive to us at the moment. So we can, that's because this program's running. Over here you can either press pause and the figure opens up, or you can press Control C. Okay, which terminates the program. Okay, so now let's write our simulation code. What are we going to do first? We're going to plot first, then we're going to update the positions and the velocity. So update the velocity, then we're going to update the position, and then we're going to check the boundary conditions. So what does that mean? Well, we're just going to have periodic boundary conditions, which means that if we've got our figure over here, that means that if particles go over to the right hand side, they just come back in on the left hand side. If they go down the left hand side, they're going to come back on the right hand side. And also, we're going to do this trick. So we have particles starting at the very top. They fall down, 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 down. Once they reach this bottom part, instead of just creating new points at the very top, we're just going to reset the points. So they're going to fall, 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 and then reset them at the top, and then fall, 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 and then they'll sort of randomly move around. And it's going to give this illusion of continuous rainfall. Okay, so there we go. We're going to create functions that do each of these things. So the first function we're going to do is it's going to update the velocity, but we can create the plotting function already. So we know they're going to have position X and position Y. Okay, and we're going to want blue points. And let's just say marker size, I don't know, let's say 20. Okay, so we've got our function. The first function that we've got over here is going to be updating the velocity. So remember, how do we create a function? Well, we tell MATLAB that we're doing a function, we're creating a function, and then we need to tell it what our output is. Well, we want to update the velocity, so we're going to have a new velocity. Okay. We need to pass it the previous velocity. We need to pass it the acceleration, and then also the terminal velocity. Okay, because we don't want these particles forever accelerating to the point where they're moving so fast that they don't even appear on our screen. So we're going to have to define some sort of terminal velocity. Now you guys can play around with values for that, but I've got some coefficients that I played around with before, and I think they work quite well. Okay, so what's going to happen? Well, how do we calculate our new velocity? Well, our new velocity is just going to be equal to our previous velocity plus some acceleration term. Okay, will be defined over here. And then I won't use the terminal velocity just yet, but we'll keep that argument there just to remind us that we need to implement that function. So over here, we're going to calculate the velocity for x. Okay, tab complete didn't work there. The previous version of velocity x, our acceleration is going to be wind, right? So over here, wind isn't actually a velocity, it should be an acceleration. Okay. And for now, let's just say the terminal velocity is 0 because it's not being used. We'll do the same thing for y. Gravity, still not using the terminal velocity. That should be fine for now. There we go, so our velocities are updating. Now what do we need to do? Well, we need to update the positions. So let's create a new function. I don't know if you guys can hear, but I've got my dog sleeping just right behind me, so you can hear her snoring every now and again. Update the position. New position is equal to, it's going to be the previous pose plus the velocity. This was going to be quite simple. It's going to be new position is equal to previous position plus the velocity. Now the benefit in creating these functions are that we don't have to copy and paste this code for each of these pieces of over here twice, okay? And it also means that if we've made a mistake, we can just update it in one position rather than have to track down where are we doing this piece of code in our function. So we just have these modules and we can just update the modules themselves. Okay? So let's update our positions. We go, updating the position, perfect, and then we're gonna, our final function is just gonna be checking the boundary conditions. So what are we gonna do? We're gonna reset the position x, position y, okay. Okay, we're also going to have to pass to it the map width and map height. Perfect. So just again, this yellow highlight over here is just telling us that this variable is being unused. Maybe it's worth just deleting it and then forgetting about it, but this highlight's also reminding us that, hey, we've got to do some code because we do want this variable used later on. Okay. What we say. First check the x boundaries. Okay, so we're going to check where are the particles off the screen on the left hand side. So where are the particles positions less than 0? So remember, so x starts over here, so it's x is 0, and then the maximum width. Where are the particles off the screen on the left hand side? So where are the position x values less than 0, less than the left hand boundary? Well, wherever that is true, we want to set those now to the map width. Okay, so we want to set all those particles that have gone off the screen on the left hand side over to the right hand side of the screen, because their velocities are carrying them further to the left, which means that they're going to move further in on this side. So we're going to get these cool particles moving around, and then the same with the particles going off on the screen on the right hand side. Map width, we're going to set them to 0. Their velocities have gone further off to the right. Okay, just one more. We don't have to worry about particles going off the screen up the top, because gravity is always pulling them down and there's no velocity pulling them further up. Maybe that's something that you can incorporate in yours if you want to add some more realistic wind. You can blow the particles up and also further down. But I'm not going to bother with that for now. So where have positions gone less than 0, we're going to set them back to the map height. Okay. Misspelled height up here. There we go. Map height. There we go. So the checking's working. Let's update those positions. Perfect. Just one more thing to do. Over here, I'll show you. While this is all correct, everything should be working, our plotting won't be working at the moment, and that's because we've opened up the figure and we're plotting, but we're constantly running in this while loop, so there's constantly things for MATLAB to do, which it prioritizes higher than updating the plot. So it actually plots the canvas, but it's just overriding each time that it's plotting. If we want to force it to draw, we're going to have to use the draw now function, but I'll just show you what happens. Let's put a bit of an arrow over here, velocity X. Oh, it should be wing. There we go. Okay, so you can see the program's running at the moment, but it's not actually updating at a plot. A plot's not even been open. So if we pause this, click debugging, there's this figure. Okay, we want to draw now. There's actually something else we also want to do. We want to fix our axis. So if we open up our figure, when we just draw our points, what it's doing is it's just drawing our points and always trying to center them in the very middle. But we don't want to just follow the reference frame of the particles as they're following, because that just means the particles are going to stay in the center. I'll show you what happens. There you go, so you can see that the particles are always in the center. Okay? There you can see that they're falling, but the particles are always staying in the center. So what we're going to do is we're going to fix our frame. Quick debugging. Sometimes it just opens up the last function that was running. Quick debugging. That's fine. So just press Ctrl C a couple of times until it finishes. Yeah. So we're going to draw now. Bless you, Nala. Zero. So axis just sets up plot axis. Axis map width. Height. There we go. So now it's setting our reference frame to be the map, and you're going to see that these particles just start falling exactly where we want it. Perfect. Okay, but you can see that there's very little randomness. There's no randomness actually in the way that they're falling. So let's introduce some randomness. Spice up this simulation a little bit. Just Control C until you're done. It is a bit of a hacky way to sort of enter program, but this is what we have to do when we've got this always running while loop. Okay, so what can we do to introduce some sort of randomness? Well, we can change the wind direction. Okay, so we can introduce a counter, and then once that counter reaches a certain value, let's say above 10. Actually 50. Okay, then we're gonna set the wind to be a random value. Now, if we just produce random values, you can see they're between 0 and 1 by default. Okay, but we want our wind to be able to go in both directions, so positively and negatively. So what we can do is we can do a trick. We can go rand minus 0.5. Now, we're going to get values, rather than between 0 and 1, between negative 5 and 5. Okay? Sorry, negative 0.5 and 0.5. Okay? And then we're just going to reset our counter. So we're going to increment our counter. Once the counter is greater than 50, update the wind, and then reset the counter, and so that we can, every 50 iterations, update our wind. Great. Now let's implement this terminal velocity. So we're going to check where are the velocities too large. Where is our velocity? So we need to check what's the absolute velocity, and if it's greater than our terminal velocity, then we're going to update those velocities. So let's go new velocity. Wherever they are. We're going to fluctuate our particles around that terminal velocity, but we're going to go terminal velocity, set them to the terminal velocity, but then fluctuate them around that. How do we do that? Well, we're going to create random values. And we want the dimensions of these random values, and we want the same number of points as there are values too large. So we go over here, new velocity. Okay, so this looks like a bit of a mess. What we've done is we've said how many points are there whose velocity are too large. Okay, grab that size and now create that number of random values, and then that way we're just going to fluctuate our points around this terminal velocity. Okay, perfect. That should be it. Let's increase the number of points we've got and see what it looks like. It's quite slow to start. So I see what's happened is we have this position X and position Y variables don't have the exact same dimensions. And so what's happened is MATLAB has misinterpreted what size position X should be, and rather than making it a vector, it ended up creating a matrix. I'll show you. So we've got this. We can add a breakpoint over here. Once we run this, you see that, okay, position X has a different set of dimensions to position Y. And once the simulation starts, it actually forces position X to be, let's break one over here now, continue, run through once. Position X is now 1000 by 1000, so it's a matrix. It's a lot of points to for it to loop over, and so yeah, 1000 by 1000 is a lot of points. And so it doesn't like that, it's very inefficient. So what we need to do is we actually need to transpose this this array over here. So rather than having it be an array, one row, 1,000 columns, we want it to be a vector. Okay, so add in this little dash at the end. It's a way to transpose the array. You'll see that if we now start from scratch, it should run much faster. Remove the debug point. The debug point is just a way of stopping the program at a particular point. So there we go, press run. Okay, what's going on? Well, what's going on is we still have a terminal velocity set to 0, so we can never accelerate fast at all. It's trying to go as fast as gravity to pull it down, but it doesn't like it, so let's go 20 times gravity. And let's go 5 times gravity. There we go. That's starting to look a little bit better. Put some sort of randomness in there now. The particles are falling. So you can start playing around with these parameter values now, and you can tweak this to look however you would like it to look. So when I played around with it before, I got it to look like this. So it starts off quite slow. Particles gain some momentum. I added a little bit of a 3D effect where some particles had a larger size than others. Okay. And you can see that once they start falling and they gain momentum, it starts to look a little bit more convincing. Alright guys, and that's the end of the tutorial series. I hope you guys learned a lot. If you guys have any questions, leave them in the comments, and I'll try and respond and help you guys out as best I can. Hope you guys enjoyed it. All the best, guys. Thanks.